All right, welcome Astro 7 students. Our next presentation for today's class is going to be on climate forcing and how that relates to climate timescales. So the concept of forcing has to do with heat in and heat out and the timescales over which those may change. So if you think about it, the heating of the Earth, of course, starts from, hang on, I've got to power my phone off. All right, back to you. So the heat arrives from the sun at nearly a constant rate. It only changes by about 1/10 of 1% over the solar cycle of 11 years. And beyond that, it changes virtually not at all over any reasonable human time scale. So if the Earth comes to a state where it's able to emit as much energy to outer space as we get from the sun, then we say we're in radiative equilibrium. So when heat in is equal to heat out, you're in radiative equilibrium, and if you're not, we say you're being forced. So we have radiative forcing. These are some of the forcings that the Earth gets. So we got heat in from the sun, and then we got heat out. And the energy is divided up into many different ways. Reflection off of cloud tops, off of snow and ice, reflected off the atmosphere. Those are all reflections, or the fancy word for that is albedo. Then we have heat that's absorbed by the atmosphere, but then re-radiated later in some form. And then we have heat that's absorbed by the ground and then is radiated back by the ground. So the Earth system will experience a change in equilibrium, then we've got radiative forcing. So definition. So here's the radiative forcings that we have had over the last 1,000 years. All these little dropouts here are due to volcanics. So volcanic eruptions can temporarily change climate quite a bit. So what they do is they blow a lot of aerosols into the high atmosphere, up into the stratosphere even. And the stratosphere, since there's no convection up there and there's no water vapor, then there's no easy way to wash that dust back out of the atmosphere. And it hangs up there for typically a year or two. And that's enough to deflect up to 1% or 2% of the sun coming in, and that can be enough to to change radiative forcing by several watts per square meter. For comparison, the amount of energy coming into the Earth is about 1,000 watts per square meter on a real clear day. So 2 or 3 or 4 or 5 watts is still relatively small, but it is enough to change temperatures on the Earth by several tenths of a degree over the times, average temperature over the whole Earth, over the times of these forcings. But I want you to notice towards the end here, so this is up and down a little bit, but fairly stable up until the about the beginning of the 1800s. And at that point we discovered coal and we began forcing climate. And of course then we discovered oil in the late 1800s, and it got steeper, and then smog and aerosols kind of dropped us down here, and then we passed the Clean Air Act, and things have been getting much hotter, much faster ever since. And so basically this realm over here at the end is the realm that we're most concerned with in our present and future, and this steep upward climb is due to the forcings that are caused by greenhouse gases, as we'll see. Hang on, let's go back here. So now what we're looking at is the sun and CO2 and aerosols all put together, and there was a so-called medieval warm period back here. There was the Little Ice Age in here, and then the modern warming period, and then the real large acceleration with the industrial age. So the 1880 to 1910 average has been, until recently, the conventional so-called pre-industrial period. So the pre-industrial is what we like to refer to when we study paleo data, paleoclimate, and then try and relate that to the forcings that we're doing today. So to know what the Earth can handle, we need to know what is the unforced, what is the equilibrium Earth like. And so that has been 1880 to 1910. The problem is that 1880 to 1910 is really defined only by the fact that that's when our data got pretty decent for global average temperatures. Prior to that, it was not as good, so it was kind of a convention. However, we were already forcing climate. We already had greenhouse gas emissions that were fully 10% as much as they are today back during this period. So a fairer time for pre-industrial is actually earlier, and so we'll look at that in a minute. So Schur and Mann and all did that work, and shows that a proper pre-industrial is actually lower than this. Okay, so I found a reconstruction of total solar irradiance. Sorry, that's hard to read, but what I did is I scaled these to the same vertical scaling, and so you can look at how comparable they are. And you can see that the sun does have an influence on climate. So you can see how well these peaks and valleys line up. But they kind of stop lining up once we get into the mid-1900s and other factors become more important, like the aerosol cooling that we've done through our pollution, and then of course the CO2 warming that we've done. But there have been, now I should also say there's something else involved here. The reconstruction of the total solar irradiance, this is probably not correct. It probably needs to be slimmed down quite a bit in vertical. And this is because we had trouble calibrating the number of sunspots to solar radiation. We hadn't properly realized that it was not so easy to count sunspots consistently over the past 400 years since we've had the telescope, because sunspots come in all sizes and shapes, and the little ones are hard to count. And it wasn't until some relatively recent work out of Stanford showing that if instead we took advantage of all the drawings that were done and used sunspot groups, which are much more reliable in counting, that in fact it looks like this long-term solar rise here doesn't really exist. That yes, there are peaks and valleys of about 100 years, those are real, but that the tops of these peaks and the bottoms here don't have an upward slope to them after all, and they're actually probably level, somewhat as they are here. So CO2 and water vapor and methane and nitrous oxide, and then more modernly we have chlorofluorocarbons and hydrofluorocarbons and other chemicals in the atmosphere that are all greenhouse gases, and they will trap a broad set of the infrared radiation that the Earth is trying to radiate back out into space as infrared to cool itself from the heating that's being caused by the visible light coming in from the sun. CO2 concentrations have gone up 46, actually that's more like 48% now, since pre-industrial times, and the atmosphere has also become more humid. So CO2 warmed air will hold more water vapor, and that's the Clausius-Clapeyron relation. And water vapor actually a little bit more than doubles the amount of heating caused by CO2 alone. As a note here, because we're going to talk about climate denialism later, it's one of the favorite memes of the climate denialists. In fact, I even heard this just a few months ago at a Christmas party by some guy. I said, oh, well, gee, water vapor is more important than CO2, ergo we shouldn't worry about our CO2, party on, etc. Well, the fallacy there is that it's the CO2 that allows the atmosphere to get more humid. So water vapor will rain out. So when water vapor gets too high, it just rains out. We, after all, have the atmosphere in contact with a ground that's 70% covered by water. So that's actually not an argument at all. There's no hint that global humidity has gone up all by itself for no reason. What allowed humidity to go up is the warming caused by CO2, which has gone up a lot, and which does not rain out. You can click on these animations and see how temperatures have warmed globally in the last few hundred years. I won't do that here, but I referred earlier to this really interesting paper by Michael Mann's group, Schur Mann et al. In 2017, and they looked at a broader set of pre-industrial temperatures and determined a new baseline. And their baseline change for greenhouse, in particular for greenhouse gases, indicate that in fact we need to add almost 0.2 degrees, 0.2 degrees centigrade. I guess I should say subtract from the prior assumed pre-industrial baseline in order to get a proper baseline pre-industrial. So in other words, it's hotter than you think. 2 degrees. Yeah, so much of our modeled temperature data depends on paleo data, and we need true paleo data, meaning non-human forced, in order to make more accurate predictions of what's going to happen in the future. So it is actually pretty important to find a proper pre-industrial baseline. So this actually does make a lot of sense. Okay, it has a 0.25 here. That's actually, that should be 0.20. So 0.25 refers to a different calibration from mid 20th century. I got to change that. Why didn't I notice that? Mid 20th century average temperatures to the old pre-industrial 1880 to 1910 baseline. So here's the greenhouse gas forcings that we're most interested in. So CO2 has a vibrational band, very broad, which cuts deeply into this red curve, which is the black body emission, the thermal radiation that the Earth is trying to emit back out into space. So the red curve is the thermal black body spectrum for an object at 294 Kelvin, which is roughly the temperature of the Earth. So right at the peak where the Earth is trying to emit the most radiation to outer space, the only place that we have to dump our heat that we get from the sun, there's this big fat and fattening CO2 band. Then there's ozone out here, not as significant, but still significant. And then mixtures of methane, nitrous oxide, and then especially water vapor. So water vapor blankets quite a bit up here and also quite a bit down here. And the sum total of the water vapor absorption over here on the short wave number side and here in the long wave number side actually a little bit more than doubles the CO2. So we're being forced warmer, and that's because of the rising CO2. We're pumping CO2 into the atmosphere 100 times faster than it used to be. The pre-human CO2, net CO2 source was volcanoes, and we're outdoing volcanoes by a little more than a factor of 100. And that's far more than the Earth can digest in the form of absorbing it into the oceans or absorbing it into land plants. So it is true that more CO2 will help plants grow a little faster. They do produce more body mass. Doesn't mean that the crops they produce are more nutritious. In fact, they're less nutritious. But anyway, it is true that rising CO2 does produce more plants, and they do help take out some of that CO2. But a good half of the CO2 that we emit can't be absorbed by the ocean or plants, and so we end up with this net forcing. CO2 levels in the atmosphere have gone up about 48%. So we are out of radiative equilibrium by about 0.58 watts per square meter, half a watt per square meter. By the way, that number, 0.58, I'm going to leave it into this PowerPoint, but we're going to see later when we look at more recent research that this number has been revised upwards, and it's more like 0.85. So this is the source of our primary driver, our primary forcer, and it's CO2 emissions by the world divided up into regions. You can see China here is the real problem lately. And there's been ups and downs and recessions and so forth, but net, this is just going up steeply. And so the CO2 in the atmosphere is going up steeply. And I've put in some bars here to try and guide your eye, and just to make sure you notice that recently we have taken a sharp upward trend in that. We're going up now at about 3 parts per million per year in CO2 concentration, and back here it was more like 2 parts per million per year. So the solar revolution and so forth is all sounds like great cheerleading, but in fact it's not helping. Okay. Human-generated greenhouse gas radiative forcings as of 2014. So this is the IPCC's assessment report number 5. So most of it is CO2, 58%. Some is methane, some is nitrous oxide, some is ozone. In fact, this number is pretty badly underestimated by recent work, which we'll come to later. But there's a total, anyway, as of 5 years ago, 6 years ago. Probably not accurate, probably too low, but at least there it is. Radiative imbalance, when you do the addition and the subtraction from the sun coming in, that's what you get. Another forcing is from food, agricultural, and land use, and I seem to always have people from the sort of ecological, organic, be kind to cows group who'll want to point out that livestock dominates, but it really doesn't. Okay, there was a badly done film a while back called Cowspiracy, which didn't do their numbers right, and unfortunately, well, their goal, I think, is laudable, to be nice to animals, and we need less meat and eat lower on the food chain and so forth, but it's not really true that agriculture dominates, but it does make up a significant amount. So yeah, there's recent work. Ettenmann in 2016 did more accurate calculations of the radiative forcings. These are just calculations of the forcings from methane and nitrous oxide. And these show that even for constant concentrations, just merely the calculations of where they interfere with incoming and outgoing radiation shows that the radiative forcings are about 23% higher than the IPCC values had assumed. So that's not good. And then newer work still is even more alarming, because Thompson et al. Showed that emissions of nitrous oxide were accelerating much more than people had thought. They were underestimated. And then Wilkerson et al. At about the same time showed that ocean emissions are up 200 to 500% higher than the earlier work had assumed. And the earlier work was based on much more limited fine-scale, small sampling at the surface of the ocean. And what Wilkerson et al. Did was they used airplanes and more advanced instrumentation and flew over much more of the ocean and got a much more representative view. And they find much more nitrous oxide coming out of the ocean than we thought. Now, prior to this, we thought the oceans contributed about 26% of the nitrous oxide emissions. So that's significant, 26%, and now we're going to have to take that and we're going to have to raise it by a factor of several. So this is brand new. I did not run across these papers. I thank a colleague of mine in Germany who brought these to my attention recently. But these are too new in any case to have been incorporated into any climate models or radiative forcing calculations. Okay, let's talk about a feedback. Positive feedback and negative feedback. I'm trying to force myself to instead use amplifying feedback because I think it's language clearer. Positive feedback, unfortunately, we scientists realize now, oh gee, well, average persons, they hear positive feedback, they think, oh, we love positive feedbacks, they're great. No, we don't mean positive in terms of happy, we mean positive in terms of the mathematical sign of the front of that term in the differential equations that describe the forcing. Positive feedbacks are bad. Negative feedbacks are good. Negative feedbacks tend you towards stability. Positive feedbacks amplify you in the initial direction. So if you're headed towards a forcing that's warming and you have a positive feedback, that is a bad thing because that means you're going to warm even faster. Unfortunately, virtually all the climate feedbacks are positive feedbacks. Also, they are feedbacks, meaning they act on a term that includes within it the term, let's say the forcing of the primary forcing. Let's just put it that way. So if that primary forcing goes away, then it doesn't matter whether you got a plus or a minus sign on it. It's not going to contribute. And the point of that is that an initiating forcing cannot be reversed by merely reducing changing the sign on the feedback. I didn't say that right. A negative feedback can't change the sign of the net effect. That's what I wanted to say. There it is right there. So, in other words, suppose that you're talking about the albedo feedback and you're worried about the fact that the ice in the Arctic Ocean is disappearing. And the fact that the ice is disappearing means that you're exposing more ocean, dark ocean, to absorb more sunlight, and that's only going to amplify the warming of the ocean, and that's only going to melt the ice faster. And yes, indeed, that's a positive amplifying feedback. But what happens when the ice is all gone? Well, when the ice is all gone, then the feedback goes away as well. There's no more feedback. There's no more additional change to the temperature of the water. So that's what I'm trying to get across here. So a negative feedback cannot reverse the CO2 warming. Even if you have a negative feedback, it's only going to operate if you still got that positive thing you're trying to get rid of. But once you've gotten rid of it, then it ain't going to help anymore because you've gotten rid of the term onto which the negative feedback is applying. And I know that that's a little awkward and it may not get across, but I do have a question in my test bank, so I feel like I should say that. So one of the things about climate feedbacks that we don't understand very well is cloud feedbacks. So we already talked in an earlier PowerPoint about how clouds were the most difficult thing for us to model and to get right. And the reason is because they exist over such large spatial scales. However, there is plenty of evidence to suggest that clouds will show a positive feedback, that they will actually amplify the warming. But I do have to give credit to my friend Tim Garrett and my even longer term friend Steve Kruger, who I've known since we were graduate students together at UCLA, who did work a couple of years ago, and they show that clouds will actually break up in such a way that they will have a zero feedback, at least tropical clouds, tropical convective clouds, in a warming world. And that's at least one study that is a little more encouraging. Whether it's right or not, we don't know. Too much evidence to the contrary, so I'm not really willing to put my bets on the Garrett and Kruger work yet. Okay, so I want to show here the close correlation between forcings and global average surface temperature. So the surface temperature is red, and we're going to talk about this graph going from 1880 to the present in the next slideshow. But anyway, notice that it goes up, and then it levels out, and then it goes up again. And that's the same thing that the sum of all climate forcings we're doing as well. The big dropouts here, again, these are due to big volcanoes. So there's Mount Pinatubo in 1992. There's Mount Agung in 1963. And let's see, there is Krakatoa, east of Java. And there's Santa Maria, the largest of the 20th century volcano in Alaska in 1902. So now the next and last big thing that I want to talk about that I think is very important, because this is very human-centric: time scales, human versus physics. So the ability to achieve radiative equilibrium takes time. So if the forcing is happening on a significantly shorter time scale than the physics time scale of the system, then the equilibrium may be impossible to reach. The system just can't catch up. It can't catch up to this rapid forcing. That's the situation that we're in now. We'll remain out of thermal equilibrium, out of radiative equilibrium, until we can slow our emissions down dramatically. This is showing 65 million years of climate change. We talked about some of this. We showed this graph once before in the Paleo chapter. There's the Paleocene-Eocene thermal maximum, closest analog we can find for rapid climate change, even though it was 100 times perhaps slower than what we're doing today. The ups and downs here have to do with glaciation and CO2 levels, and we're now in this rapid up and down period of the ice ages, because CO2 has gotten to a low enough level, forget about the last 100 years, but gotten to a low enough level that the ice caps have formed and are rather sensitive to the CO2 level. Now we're doing not 65 million years, but less than 1 million years, and here's all those ice ages now spread out. So we ended the last ice age and we got out of it, and then here we were, CO2 at an interglacial. This is the highest CO2 levels that we'd had for millions of years, about 280 parts per million. Now look at what we've done. We're now up at about 415, right about where the red dot is. And the projections on the business as usual scenario is by the end of the century we'll be way up here. So it's far out of range of anything that the Earth has seen for millions of years. The forcing that we're applying is huge. That's the takeaway from that slide. So what is the physics time scale for Earth climate? Well, with this rapid forcing, it's shorter than you might think, but it's still, unfortunately, rather long. So I'm just going to cut to the chase here. 50 years, very round number, for significant climate change. Okay, in 10 years, you wouldn't expect significant climate change, even with what we're doing. In 100 years, yes, definitely, and even in 50 years, we expect large changes to the Earth. We're slowed down, again, by the fact that the ocean is so much more thermally massive than the atmosphere. And so the atmosphere can only react really as quickly as it can drag the ocean along with it thermally. Still, the surface ocean's the part that's most significantly affected, and 50 years is the scale. And my analogy for that is an iron skillet, and how impatient we can all get trying to cook on an iron skillet. You got to be patient and let it all warm up before it finally cooks your food. And then you got to anticipate and cut the flame off long before you're done cooking. Otherwise, if you cook right up until you're happy with it, and then turn it off, and then go off and do something else, you're going to come back and find that your dinner has been carbonized. I've had that happen. It's not fun. Okay, so this is something you will probably need to remember for your quizzes. Acceleration goes as force divided by mass. That's straight out of Newton's second law. That's just plain old mechanics. So now we're talking about velocities, not thermal. So there it is again. Time scales, in other words, delta t, time scale, amount of time, that's an amount of time, goes therefore as mass divided by forcing. It's harder to push big things. Now mass goes as size, diameter, cubed. We live in a three-dimensional world, okay? So there's the cube. So time scales go up rapidly with physical size. Big things evolve slowly. And that includes also civilization. Civilization can't act quite as fast as you might think. You might be able to panic and do something, but civilization is going to panic a lot slower. Now for temperature change, which is what we're worried about, it's thermal mass that's important. So this might be a little wonky, but there's the equation that goes with it. Thermal mass is kind of in the bottom here, thermal density. Conductivity is how rapidly heat can move through something, so you have to put these on opposite sides of the divisor. This is the rate of change across space for the heat content. And that's the rate at which it changes. So this is the heat equation. So I think the most important thing to take away from this second half segment of this chapter, the time scale for significant change goes as the thermal mass divided by the forcing, thermal forcing. And then the next most important thing, I should say, is that the current climate change time scale is about 50 years, and it's very unfortunate because it falls between the cracks for us humans. 50 years is the worst of all possible time scales, in my humble opinion. If the time scale for significant change were many centuries, we could legitimately neglect it and let smarter, more emotionally mature, more technologically advanced, more politically advanced peoples of the future deal with it before irreversible damage happened. If it were, on the other hand, just a few years, like impending World War II, that would also be good, because then we'd motivate. We'd realize the house is on fire, and we'd stop what we're doing, and we'd do something about it. We'd do what was necessary, even if it meant spending 10, 20, 30% of global GDP to slow or maybe even halt climate change before it wrecked our planet. If it were less than 4 years, you might even get our politicians to be motivated to focus on the truth instead of payoffs from big oil. Unfortunately, it's not less than 4 years, it's 50 years. It's long enough that our politicians, who are old white people for the most part, are going to die. And so they don't care. Economists studying how aggressive human behavior studying how aggregate human behavior values are rewarded in the future, have this term called the discount rate. And when you look over large civilization timescales and big corporations and big nations doing big decisions over long timescales, the discount rate is about 3%. For you as an individual, the discount rate's probably much higher than that, 5, 6, 7, 8, 10%, 20%. Kind of depends on the context. If it's something like food, the discount rate would be enormously higher because you care about eating today and not about eating next year. You worry about next year when it comes. But anyway, 3% is still, unfortunately, a very high number, because 50 years in the future at a 3% discount rate means that you care about 50 years in the future at only 23% of what you value today at. And that's not enough, unfortunately, to actually go out and take action. The year 2100, worse still, is valued at only 8% of what you value today at. Or let's say not you, but our civilization values the year 2100 at only 8% values today at, or tomorrow. So in other words, 50 years is long compared to human attention spans, unfortunately. It's also short, unfortunately, because important human timescales happen less than those 50 years. Your children and future generations need for you to act now. If you act only when things really begin to look bad, it's too late. Climate has inertia built into it. It's a large system. It evolves slowly. So how do we get out of this? Well, we have foreheads. We can think. Unique among animals, we have the ability to grasp the concept of the future, the ability to abstract principles from our observations, identify those principles quantitatively, and predict our future. We invent a category of work called science, done by scientists, and it's their job to do exactly this and inform the rest of us who will want to know so we can act on it and prepare for our future. So that all sounds wonderful, but unfortunately that's not the way it really works. We don't like what the scientists are telling us, so we throw rocks at them and we ignore them. And only if they produce more bling, more status-seeking stuff, more money, do we smile at them. And yeah, that may sound cranky coming from a scientist, but you know what? It's the truth. And I always like to just tell the truth. I'm not the only one who feels that way. It's worse than you might think, because the climate feedbacks that we'll discuss are happening now and will be locked in to a large extent for the future. We already talked about one of them with my first PowerPoint that I put on audio, and that was the ocean-atmosphere connection, and how we're very close to a tipping point for the shutoff of the global thermohaline circulation. And once it's shut off, you ain't getting it back. Okay, that's just one of many. So we speak in terms of committed climate change that you cannot change, that it's going to happen with you no matter what you do in the future, short term. What our choices are now is to try and make the future less bad than it will be if we continue on our current path. So there's another thing I need to tell the average person, and that is, if you're consoled by the idea that, well, if we just stop hurting the earth, then the earth will forgive us and the earth will heal. It's so progressive, it's so eco-friendly, it's so, hippy-dippy from the 1970s. And for some things, that kind of can work. If you stop cutting down the rainforest, then the rainforests, at least parts of them, can grow back. If you stop killing the condors can come back, and the tigers and so forth. It's not true of climate. I wish it were, but it's not. We'll see why in later shows. So, yeah, that's us. Okay, so that's it for today. I have to now go to my Canvas and talk to my students, who hopefully will be watching this maybe sometime later tonight. Okay, and for the rest of you out there in YouTube land, I hope you learned something from this. I'm always happy to hear your comments.